Hey everyone, and welcome to the second lecture in mirror symmetry by Eric Zaslow. Please go ahead.
Okay, thanks, Daniel. Welcome back, everyone. I thought I would begin with a recap of what we did last time. It's always great to, in any curriculum, to circle back, especially in such a short course that goes at such a fast pace. It's important to not leave people in the wake. So here's a review of last time with some elaborations. So the puzzle that we had considered were ambiguous clock times for a clock whose hands had both the same size. So we saw that 4 o'clock was unambiguous, but this was a bit ambiguous. We didn't know if it was a little before 2 or a little bit after 10. And we realized that that problem was the same as an intersection, counting intersections of 2 lines on a torus, those lines representing the possible positions of the 2 hands. So our plan was to compute it by homological mirror symmetry. So what we had to do to start with is explain what is mirror symmetry. It's an equivalence of physical theories. For us, those physical theories were 2-dimensional sigma models. We use Euclidean time signature. And those were maps from a Riemann surface to a target space. And we were taking the target space to be a torus. And the reason why we could do that is because we studied in some detail that if we had a target of a circle, then the circle of radius r gave the same physics as the circle of radius 1 over r. And that duality exchanged the winding states of the string with the momentum states of its center of mass. So one of those is a classically quantized number, the winding, and the other one was a quantum mechanical number. The energy being labeling an eigenstate of the Hamiltonian. Okay, so those, then we did that, we just did 2 circles, and we did the duality with one of those 2 circles. And when we did that, we found that one of the dualities we can make sensitive to the size of the torus, and the other one to the shape of the torus. And that those 2 quantities were exchanged under this mirror symmetry. So we had considered tori, well, maybe just review it. Whoops. We had considered these tori of radius r1 and r2, and then dualized r1, r2. And you see that the area gets switched under the process, and the shape, which was the ratio of this complex number to that complex number, also gets switched. So the first torus is that we're gonna pay attention to its area encoded in this 2 form that you integrate to give an area of tau. And then the next torus, we're going to encode its shape in terms of the lattice 1 comma tau twiddle. And then the statement that the sizes and the shapes get interchanged is the statement that the mirror map is that tau twiddle equals tau. There were a lot of questions about what was hidden under the rug to say that, oh, I have a theory that is only sensitive to the symplectic structure, omega, and one that's only sensitive to the shape or the complex structure, tau twiddle. And so there was a lot hidden under the rug. There were a lot of questions about that. Just to say, just to acknowledge that, I'll say that behind under the rug was the fact that these sigma models could incorporate fermions in a way that has an n equals 2 comma 2 supersymmetry. So 2 supersymmetry generators for both the left moving oscillator modes and the right moving oscillator modes. And that gives 2 possible nilpotent operators, Q, that square to 0. And so this topological reduction means that we can replace our Hilbert space. I had said with ground states, but in a more general context, we replace it with the Q cohomology. So states which are killed by Q, modulo states which are Q exact. And then in such a scenario, the path integral can localize to the Q trivial configurations. And depending on which type of supersymmetry you have, those Q trivial configurations will be either the holomorphic maps for the A type and B, or the constant maps. Okay, and what we did was, I think I already reviewed this, that we did the T duality in one of the two directions. Okay, any questions on what we covered last time? Okay, while you're mustering the courage, while you're mustering the courage to ask a question, I'll continue, but I'm happy to entertain them at any moment. So here's a comment for Daniel had requested this this direction, although this is not going to be the focus of these lectures. So this duality that we did, we performed this T duality or circle duality on this direction. I'm just going to make this direction the vertical direction. So there's a reason why I did it horizontally here, because we typically think of that complex number tau as this is the imaginary direction. But I'm just going to tilt my head and so make the circle direction that we dualize the vertical one. And we can do this more generally. So if we have 3 vertical circles, which means that we have a 3 torus, we can dualize each of those circles. And an idea is to try to do this in families. So if I have a family of 3 tori over some base space, so some base space parametrizing the 3 tori, and then I have a family of them. So for each point in this parameter space, I get the 3 torus that it describes. In our example, it was just a 1 torus, but that's okay. Then I could try to perform the T duality for each of those torus directions over the same family of tori. And so I would get, instead of S1 R, I have S1 1 over R if there were just one of them, or if there are 3 of them, I could do that for each of them. When we replace R by 1 over R, it's equivalent to replacing the torus by its dual torus. Dual torus being the set of U1 monodromies around the torus. So if there's just a circle, you have to specify, if you go around the circle, maybe you have some phase change described by some monodromy in U1. And so that gives you a dual circle, the possible elements of U1 that you get that way. So U1 is also a circle, and you get the dual circle. When you pay attention to what are the sizes of these circles, in fact, R goes to 1 over R. So mathematically, what we've done is we replaced the circle back here, this R1 circle, by its dual circle, 1 over R1. I shouldn't do it that way. Okay, so that's some explanation of what this T duality procedure does if you happen to have a family of tori. So now that was the story before we considered boundary conditions, and our thesis was that any physical equivalence had to respect all the structure, and part of the structure was all the possible boundary conditions that you can place on this string. So let me remind you just the classical free string. So this is the wave equation. For U being some amplitude of a one-dimensional string in some transverse direction. And the solution to the wave equation 1 dimensions, I already alluded to these left and right moving oscillators. This is the general solution. You take a function f and a function g, And then you propagate F moving to the right, I guess, in this, and you propagate G moving to the left. And that's the solution to the wave equation. You can take any impulse in any direction, you get a wave. So if you impose a boundary condition, so here's a key point. If you impose a boundary condition, what does that look like? It means taking the spatial direction. Let's say the boundary is at the x equals 0. And I want to, let's say, pin down the string at its left boundary. So that'll be a Dirichlet type boundary condition. So let's say I require that u at the boundary is 0. So plug this in to our solution, our general solution, and you see, well, if I plug x equals 0, I get f of t plus g of t is 0, or f is minus g. And this is true more generally. Algebraically, what that says is that the boundary condition is relating the left moving and right moving parts. And those left and right moving parts form the left, are described by the left and right oscillators of the string. And it's true quantum mechanically. So some boundary condition relates those two sides. So what that does is, what that says is that if you had started with a 2, 2 supersymmetry, and then you have a boundary condition, you have half of that. So just an n equals 2 supersymmetry. And so you get to choose. Either your boundary condition can preserve QA or QB, one of those two types of supersymmetries, but not both. And there were some questions about then, so what does that mean? That means that the boundary conditions will look differently in the two types of supersymmetries that you preserve. So when I impose on my boundary condition that I preserve A-type supersymmetry, these are the geometric equations that result. I get a Lagrangian submanifold of a symplectic manifold whose size was this omega 2 form. For us, we don't have to worry too much. I'll talk a little bit later. Lagrangian in 2 dimensions is an empty condition. So we just get a one-dimensional submanifold with a flat connection. That part I'm also happy to sweep under the rug for a while, at least. On the B side, we get a complex submanifold. It's sensitive to the complex structure, which was described by this shape. And we called that tau twiddle. And so the the boundary condition is that the Dirichlet type boundary conditions are that the string has to end on a complex submanifold. Or that complex manifold could be the whole entire thing. Again, there's a gauge field, and that gauge field has to be a gauge field for a holomorphic instead of a flat bundle. Okay, I will be discussing a little bit of the geometry of what Lagrangian and holomorphic means a little bit later on. But at a high level, we can say, okay, when you add boundary conditions, they impose some geometric conditions on the ends of our string. And these are them in the two cases. And so the mirror symmetry interchanges these, and it interchanges the boundary conditions. That's a simple statement that has some profound consequences. So let me review that. So suppose I have two pairs, a mirror pair, X and X twiddle. I can consider A or B on either side. So let me consider A for the moment on X and B for the moment on X twiddle. Well, X twiddle is a complex manifold. And the branes, the boundary conditions, are submanifolds that are complex. And there's a distinguished submanifold of a complex manifold, which is just the point. And that's a complex submanifold of dimension 0. It's kind of a trivial case, but it's there. And now the mirror philosophy says, well, there must be some dual brane on the other side. Like we said, objects have to map to objects under an equivalence that respects all the structure. And the structure, as we had seen, is a category, and the category is contained of objects of boundary conditions. So those boundary conditions have these geometrical descriptions. So there must be some geometrical corresponding boundary condition to the point. Does it make sense? I'm waiting for some question to arise. This is from my perspective, one of the key points in understanding mirror symmetry.
Can you explain again?
Sure. Let me recap what we learned. We said if there are mirror pairs, then they have to describe equivalent theories. That's what we mean by mirror symmetry. And that equivalence must respect all the structure of the theory. That structure is encoded in part by this set of possible boundary conditions. Then there was this thing swept under the rug, or what are the possible boundary conditions? Well, I said, well, there are two types of boundary conditions that can preserve the mirror symmetry, and they're exchanged under the mirror. And one type focuses on complex manifolds, and the other one focuses on the symplectic structure, and the boundary conditions are half-dimensional submanifolds. So in the case of the two torus, the boundary conditions would just be lines or curves on the two torus. Okay, complex manifolds are always even dimensional. So if I have a complex manifold X twiddle, it always has a distinguished zero-dimensional submanifold, which is just a point. Actually, there's a whole family of points, but the points are kind of stand out. And so those are submanifolds. Those are possible boundary conditions, namely that you pin the end of the string down to a chosen point. And it must correspond to something on the other side. We don't know what. So that's the argument. And let's try to see if we can figure out a little bit more about this thing that the point corresponds to. Okay, I'll ask you a question. What is the moduli space of possible points that live inside X twiddle? Namely, what are the choices of point, the space of choices of point in X twiddle? I think I'm going to refuse to proceed until somebody attempts to answer the question. Or ask a question, or utters something at all.
X tilde itself?
Ah, great. Yes, we have an answer. Thank you. And a correct one at that. Well done. So what are the possible points inside X twiddle? They're described by X twiddle itself. That's all X twiddle is. It's the set of points. So the moduli of possible points is X twiddle itself. So that should be the moduli of possible, whatever this dual object is. But note, if we had access to this dual object and we were over here in X and we knew how to find it's this dual object, we look at its moduli space and we get X twiddle. So it's a geometric way of finding the mirror if we didn't know it in advance. X must contain some object mirror to a point, and its moduli space has to be that mirror manifold. That's it. So we immediately pounce upon a geometric construction of the mirror. In fact, we can, this is what I'm saying, if we can find this mystery object, its moduli space gives the mirror. Okay, well, whatever that mystery object is, it's a pair of Lagrangian submanifold and flat connection. And we have some information about the mirror, namely that its dimension is 3. For Calabi-Yau threefolds. So those are the geometric manifolds where mirror symmetry was first discovered. So if it's a threefold, then its moduli space has to be 3-dimensional. But you can actually compute, given a Lagrangian submanifold, what is the dimension of its neighboring Lagrangian submanifolds up to equivalence. And that turns out to be given topologically by the Betti number. So what that tells us, the number of one cycles, or independent one cycles on the space. What that tells us is whatever this 3 manifold is, it's starting to look like a 3 torus. It has 3 independent one cycles, just like a 3 torus does. We can go even further. The moduli space of pairs Lagrangian and whatever this flat connection means, has a forgetful map where you just forget about the flat connection. That seems silly, but you can do it. That means that there's some such map. But we know something about that map, the fiber of that map, namely, if you give the Lagrangian, what are the possible connections that you could have forgotten? That itself is a torus. These tori are popping up all over the place. Why is that a torus, the possible flat connections? Well, as I said, a sort of quick, one way to describe a flat connection is to say, well, as you go around a loop, you have some phase shift that the flat connection describes, some monodromy. And that was given by an element of U1. But you have one of those circle elements for each loop that you have. So if you have 3 loops, because the first Betti number is 3, then you get a 3 torus. So that means that the moduli space of this thing has the structure of a 3 torus fibration over some space, geometric space. If this was a torus already, then this space of possible fibers is the dual torus. So this says that every moduli space of branes has the structure of some torus fibration. In particular, what we saw was that the dual space is a moduli space of branes. That was our discovery back here. This moduli space of point is the same as this moduli space of the mirror of the point. So that means that the dual moduli, the dual mirror, the mirror dual is looks like a torus fibration. But the same reasoning says that X must also look like a torus fibration. Just take the same reasoning, swap it the other way around. Could have started on the other side. So this suggests that torus, that the mystery brane is itself a torus fiber of the torus fibration, because then it would have a 3-dimensional family of branes. And it suggests, and then as you construct its moduli, that 3-dimensional family, the moduli of that torus fiber as a brane is the dual torus fibration. So that's the conjecture that Daniel wanted me to say something about. We arrive from somewhat naive reasoning at the conjecture that if you have 2 Calabi-Yau 3-folds participating in mirror symmetry, then they can be described in some way as a Lagrangian torus fibration. And they're related by the fact that those torus fibrations are dualized under mirror symmetry, which is just doing that R goes to 1 over R in families. Okay, so that's a nice slogan that you can take away with. Mirror symmetry is T-duality. But I guess the point of the talk is to do a little bit more explaining than sloganeering. So I'm going to come back to that part. So what we had seen already last time is that the boundary conditions form a category. Maybe I'll go a little bit quicker through this part. The objects were the boundary conditions that we've discussed. And on the A side, those boundary conditions were these Lagrangian submanifolds and these flat connections. And we can ignore that flat connection part for now. The morphism spaces, I was describing them as the ground states when you have a boundary condition on both sides. So the morphism spaces I described as the ground states of the sector of the Hilbert space that has the boundary alpha on one side and beta on the other side. But if alpha means that you have to map to L and beta means you have to map to L prime, and L prime are half-dimensional, then the ground states would be the 0-length strings at the intersection points. So that described the Hom space as a copy of C for each intersection point. And the compositions we saw were mediated through these types of diagrams, which I'm pinching the ends together to represent that these are intersection points of these Lagrangians. And I told us, although did not derive, that the path integral reduces to just the holomorphic maps, the complex analytic maps from this disk, which is some sort of curvy triangle, or I can take it to be a straight triangle. That's a mathematical statement. And yeah, so the composition of P and Q, which I'll write Q composed with P, is obtained by summing over all possible maps like this, weighted by the area of that map. The path integral told us to weight by e to the area, because if you'll recall, something that the action was given by the integral of this complexified omega over the surface, technically pulled back, but there you go. Okay, and that category was we called the Fecha category. On the B side, there was another category, and it was something that was sensitive to the complex structure. Remember, the B side was the complex plane quotiented by a lattice. So you have still the complex structures. You can use complex coordinates, and the different lattices, there's no complex analytic map relating those coordinates. It's kind of funny because you said, oh, you could say, oh, if I take, C mod 1 tau, C mod 1 tau, twiddle. So two lattices, one described by a complex number tau, and one described by a complex number tau twiddle. You say, okay, why not just take Z goes to Z? That's a complex analytic map, but it doesn't respect the lattice equivalence. So here on the left side, I'm equating Z and Z plus 1 and Z and Z plus tau. And on the right side, I'm equating Z and Z plus 1 and Z and Z plus tau twiddle. But because tau is not the same as tau twiddle, that equivalence is not going to be respected by that map. It's actually not well defined on the quotient. Okay, and then the category is everything holomorphic. So for our purposes, it's going to be holomorphic vector bundles. And what I want to do today is talk a little bit about the geometry of what is a holomorphic vector bundle, what is a holomorphic line bundle. So a vector bundle is like a linear space in families, and the morphisms are just families of linear maps, and the compositions are compositions of maps. So the category structure isn't so detailed in this case, but there's some details in what are the objects. So that's what I'd like to sink my teeth into a little bit today, and then I'll do the calculation in the second half. Anyway, so mirror symmetry predicts an equivalence of these two sides. On the left side, this category some of whose objects are holomorphic bundles is called given by this notion, where lambda tau is the lattice generated by 1 and tau. On the right-hand side, we have a two torus whose area is described by complex number tau, and that got complexified by the B field. That was something we discussed last time. Okay, so we need to understand the two categories equated under mirror symmetry as well as the map between them. So I gave some sketch of the objects, but I want to maybe say a little bit more mathematically about what they are. Is there time? That's for me to ask myself. I think there's some time. So here's a math break about the objects in these categories. So what are symplectic and Lagrangian submanifolds? First, we should ask, what is a manifold? The answer is it's something that is locally like Rn. So Rn is Euclidean space. That's something that we're very comfortable with. It has n coordinates. So any space which is locally described by n coordinates is a manifold. And the way we say this mathematically is here's our space or a piece of it. And we put down coordinate charts, just like if you look at some old atlas of the United States and you turn to some page, it will be a grid describing some region of the Earth. The Earth is curved, but on that region, you can identify all the points with a rectangular grid. So that's what we do. We take a region and we identify, we map it to some open set in Rn. And that's our grid for our atlas. Let's say that, call that region U alpha, call the map from our space to Rn psi alpha. And then on each, we want to be able to cover this space by such regions. So I've only drawn 2 of those regions, U beta, and then that's mapped to an open subset in Rn again. And then, of course, the reason why we can use atlases is we drive off, the page for Colorado and we, enter the page for Nevada or something. Then we go to a new page. We need to be able to relate the overlaps. And so on the overlaps, how would we relate them? So we go to some section of this overlapping section, which maybe goes over here and over there. And we have a map that goes sort of backwards to here and forwards to there. And that's this map here. And we require whatever. Certainly that map is a homeomorphism. That makes it a manifold, if you know what that word means. But if that map has more structure, then so does the manifold. If the map is differentiable, then the manifold is differentiable. If these Rn's are actually Cn's, so pieces of the complex Euclidean space or complex n space, and these maps are complex analytic maps, then we say the manifold is a complex manifold. That's what a complex manifold is. Let me give you an example. The two-sphere, where a point is described by x, y, z in 3 space. I can project that point from the North Pole down to the plane. I didn't draw the whole plane, but like that. And I get a point in the plane. So as long as that point, starting point was not on the North Pole, I determine a point in the plane. So away from the North Pole, which is some open set, I have a region of the plane. In fact, in this case, it's the whole plane. And stereographic projection from the South Pole means away from the South Pole, at least, which is an open set. I can describe that point by projecting it onto a plane up here. There's something a little bit funny that goes with one of the variables, because if you imagine sort of walking in this direction on the bottom plane, you walk in the opposite direction on the top plane. So I'm going to account for that on a minus sign that you'll see. But that's covering the two-sphere with 2 sets. And those sets are both R2, and R2 is the same as the complex numbers. So if you perform this stereographic projection from x, y, z, the point in the plane that you get when you just project it down like this, I did the calculation for you. It's x over 1 minus z comma y over 1 minus z. So it gets further and further stretched out as z gets closer and closer to 1. And you can see that sort of geometrically. Is if this point were very high, then the projection would move it very far off. I don't know. I hope I'm kind of maybe assuming that we've seen stereographic projection, maybe on YouTube at least. Okay, so this map takes x, y, z to this pair and that pair. And if we think of this as a complex number, I get a complex number x plus iy over 1 minus c. And this pair, I talked about that funny y flip. The complex number is x minus iy over 1 plus c. This distortion gets bigger and bigger as z goes to minus 1. Now let's do a calculation. 1 over w is reciprocal of this. I remove the I from the denominator in the standard way. X squared plus y squared, because x squared plus y squared plus z squared equals 1, that means x squared plus y squared is 1 minus z squared. and I can absorb this factor, factoring 1 minus z squared. I get a 1 plus z on the denominator, and it's just omega twiddle. And lo and behold, omega twiddle in terms of omega, that's this map here, is a complex analytic map. It's just 1 over, sorry, I'm calling it omega, it's W. W twiddle in terms of W is just 1 over W, which is complex analytic. You might complain, wait, it's not analytic when W equals 0, but W equals 0 is not in the point of overlap between the two. W equals 0 is precisely the excluded region when X equals Y equals 0. We don't have that projection. Okay, so we've met our first complex manifold. And sort of more generally, you just add more dimensions and they look like that. Okay, now let's meet a symplectic manifold. Are there any questions about the complex? Okay. Now let's meet a symplectic manifold. So locally, a symplectic manifold looks like R2n. It's even dimensional. And it has some 2 form locally on it. Whatever that is, it's something that allows us to define Hamiltonian mechanics, because the prime example of a symplectic manifold is the phase space of some physical system, where you have positions, and positions can live on some interesting space. For example, you know, particle, the position of a 2D pendulum has to lie on a sphere. And momentum. The momenta are just numbers, so they usually don't live in as interesting a space. The Lagrangian submanifolds I've been talking so much are just the P's or the Q's, or some of the P's and other of the Q's. These P's, those Q's. That's more honest an answer than it seems, but to make it honest it requires a little bit of mathematical sophistication to say that, oh, I can choose some variables so that whatever this Lagrangian space that I'm describing is actually just some P's or some Q's. To get us in as you know from if you've ever studied general relativity, you don't want to be tied to a particular set of coordinates. So to make this more coordinate invariant, there's our definition. When you look on the Lagrangian subspace, at this 2 form, you get 0. So for example, if the P's were all 0, this part would be 0, and then omega would be 0. Likewise, if you fix the Q's, then this part is 0. Or if you fix some Q's and the other P's, then you get 0. So as I said, more generally, the Q's could be coordinates in some space, and the P's are linear coordinates for each given Q, namely the possible momenta at that point. And that describes the phase space where you constrain the positions to lie on some manifold M. We know what a manifold is. It's called the cotangent bundle of M. Or that's a little bit fancy, we can just think of it as the tangent bundle, at least if we have some metric at our disposal, which in physics we typically do, the metric of space-time. Okay, so I'm talking about symplectic manifolds as phase spaces or things that locally look like phase spaces. And a good example of a Lagrangian submanifold that's not so simple is the graph of a of the gradient of a function. So the graph of a conservative vector field. What that means is that what do I mean by graph? I mean, take a function on M, take the ith momentum to be the derivative in the ith direction, and then you can easily see that omega is the sum. Qi describes this submanifold. And omega is dqi wedge dpi, but if pi is this, then dpi is the second derivative of f, summed over j. Hold on, should sum over j as well. df dqi, d by dqj of that times dqj. And because partials commute and wedge differential forms are anti-commutative, we get cancellation and then we get 0. So there's a non-trivial example of a Lagrangian submanifold. Forget the normal bundle. Okay, next I want to show you what a holomorphic vector bundle is. And then we will have reviewed the mathematical description of the objects on two sides of mirror symmetry. Then when we come back, we'll actually perform some calculations. So I'm going to spend a couple minutes doing that, and then we'll break for 15 minutes and return to close the deal and try to perform some calculations on these two categories. Okay, so what is a vector bundle, and then what is a holomorphic vector bundle? Well, if a manifold is locally like Rn, a vector bundle is locally like a manifold across any vector space. So I'm going to draw the pieces of the manifold as the U alpha and cross the vector space as V in that direction. Okay. So the vector bundle must locally look like that. So one piece of the vector bundle on one patch of it looks like that. On another patch of it looks like that. And then they overlap. And they overlap not just here, but on V cross there. And the requirement is that the transition functions on those overlap be linear in V. So we get a map from the overlap on the base, namely a family of matrices relating the different possible bases for this vector space. You've seen this before, the tangent bundle, namely the set of all tangent planes on a space, and we can think of the two-sphere. It's always a good example. At each point on the two-sphere, there's associated a vector space, which is the tangent plane at that two-sphere. And where that point is the 0 of that vector space. We should probably think of that vector space a little bit more abstractly, not just like living inside R3, but it's fine. Okay, so that's a vector space at each point. And then if I go to another point, I get a different vector space. And I should be able to relate those two vector spaces and figure out what these transition maps are. And that's exactly how it works. So the tangent space at a point on the two-sphere or any space, you can substitute in place of the tangent vector the corresponding directional derivative. So it's a one-to-one correspondence between vectors and their directional derivatives. And the easiest directional derivatives are those in the coordinate directions. And that forms a basis for all directional derivatives, or a basis for the tangent space. And now the chain rule just tells you if you have different coordinates, the change of basis matrix is given by here, this Jacobian matrix. Which is, of course, depends nonlinear on the coordinates, but it's a matrix, which so it's a linear matrix depending nonlinearly on the point where it is. So like you've already learned all this stuff in multivariable calculus. Now, if that happens, the Jacobian happens to be depend complex analytically, then you get a what's called a holomorphic vector bundle. And we've met that. So, and we know that the two-sphere is a complex manifold now. We found coordinates for it. The corresponding directional derivatives generate the tangent plane, but there's only one coordinate, so it's just a tangent, complex tangent line. The chain rule says d by dw is d by dw twiddle, dw twiddle, dw. So we have a 1-by-1 complex Jacobian matrix, but we know that w twiddle is 1 over w. So dw twiddle dw is minus 1 over w squared, which is a holomorphic map. holomorphic function, complex analytic function of W. And lo and behold, the tangent bundle of the two-sphere is a great example of a complex line bundle, holomorphic line bundle. So that is a possible object in our category. And in fact, replacing this 2 by any D gives us a whole bunch of different line bundles, and that D is called degree. All right, I think that's a good point to break. By now, what we've done is, well, we talked a little bit about geometric mechanism for mirror symmetry, a little bit of an aside, but it's hopefully an interesting one. We've reviewed that mirror symmetry for these two tori should be expressed as an equivalence of possible boundary conditions. Mathematically, that turns out to be a equivalence of categories. And we discussed mathematically what those two categories are. They're going to be submanifolds of the torus of dimension 1 on the symplectic side. And they're going to be complex holomorphic vector bundles on this quotient of the complex plane by a lattice on the other side. So next, after the break, I'll come back and describe some calculations that we can do, or that we have some access to being able to do. Again, sweeping a little more into the right. Okay, so actually I only have 3 or 4 slides left. So if you're worried that I'm not going to ever get anywhere, I should make it. So we have our work cut out for us. We need to show that these two categories are the same. We're not going to do all of that. As I said, we'll maybe perform one calculation. So let's look at on the A side, the one which is sensitive to the sizes. We have this 2 torus, and I'm going to draw the 2 torus as R2 mod the square lattice. So this is a fundamental domain. The objects are, we're going to take them to just be straight lines. I've said up to equivalence. You can take the objects to look like straight lines when you lift them up to R2. In order for them to actually define submanifolds, the slope of those lines should be rational. Otherwise, it's like a space-filling curve. So lines of rational slope are going to be our objects. And just for simplicity, I'm going to look at the subcategory of objects that described by lines passing through the origin. Each one actually comes in a family, and that'll be true on the mirror side as well. So we'll just take a look at these objects, lines passing through the origin with rational slope. The Ham spaces were the intersections of those lines, and that was the whole clock problem, was how to calculate the number of intersections of 2 of these lines. They're actually circles once you go down to the torus. And the compositions are made up by holomorphic triangles weighted by their area, or up to some normalization, either 2 pi I times the area. So here's a picture of how that works. So one thing to say is that in 2 dimensions, a holomorphic triangle is just a triangle. That whole complex part we don't have to worry about. By the Riemann mapping theorem, if you identify just a triangle, then there is a complex analytic map from a disk with 3 points to that triangle. So that's not even a problem. So it's really just a geometric problem of finding these triangles. So let me look at an example calculation. Suppose here's 3 lines, L0. So 0 is the slope of that line. L1, it's that line there. And this L2, this has slope 2, right? So this dotted line is at a half. So this is a fundamental domain. This is the integer points. So this triangle here, let's see what this does. This will contribute to one of these composition maps. So let's see. let's call L0 and L1. They intersect only here at lattice points. Here's L0, here's L1. They intersect here. It also intersects up here because that's also another copy of L0. We've quotiented by translation, but that's the same point. So there's only one point of intersection. I'll call it P. So this P is in Ham L0, L1. What about L1, L2? That's a little bit trickier to see. Here's L1, here's L2. Where do they intersect? Well, they certainly intersect here at a lattice point. And then this one would come up and intersect up here, but that's also just the same lattice point. Yeah, that's it. So it only intersects at lattice points. So let's call the same P, but it's now representing a different Ham space. Here, this P here is the intersection of L1 and L2. It's also the same. Yeah. So the same geometric point has two meanings for us in this calculation. On the one hand, it can represent the intersection of L0 and L1, and on the other, it can represent the intersection of L1 and L2. I could probably decorate my notation to indicate that, but I'm still just going to call it P. What about L0, L2? So what we're going to do is we're going to be calculating something like the composition, which will map L0, L1. And this is P, and this is P. And possibly to be sort of mathematically more honest, I should whoops. All right, I should have done it the other way around. I think that's the way compositions are usually written, but it doesn't matter too much. So this triangle is going to be one of the triangles that contributes. How much will it contribute? Well, P composed with P is going to land in Ham L0, L2. L0, L2 has two intersection points. So it's a two-dimensional space generated by this one, which we call P, and this one, Q. So if I was trying to do P composed with P, the answer will be a sum of triangles sort of this shape. And if they go through this point Q, this triangle would contribute how much? E to the 2 pi I times its area. Its area is 1/4. Has 1/4 fundamental domain, so it has area 1/4 tau being the area of a fundamental domain. Remember that we're using the area form. Oh, sorry. Tau dx dy. Okay. All right, so before computing the full composition, which will involve all triangles, let's look at the other side of mirror symmetry. The objects, as I said, are holomorphic vector bundles over this complex torus. And these are characterized up to topological equivalence by their rank and degree. So the rank of a vector bundle is just the dimension of this fiber V that I was talking about. So that's very easy to see. The degree, at least the degree of a line bundle, it's easy to calculate. And we can take it to be the number, write down a meromorphic section. I'll tell you what section means. And then it's just a number of zeros minus the number of poles. So a section is like the analog of a vector field. In the case where your vector bundle is the tangent bundle, then a section is just a vector field. Namely, it's a choice of vector at each point in the space. Now, if the vector is a tangent vector, then you get a tangent vector field. If the vector bundled is not a tangent vectors, but other, types of vectors, spinors or something, then you just need a choice at every point. Okay, so let's talk about that with an example. Let's look at P1, by which I mean the two sphere that we talked about earlier. As a complex manifold, sometimes it's called P1 because it's one-dimensional as a complex space. And we saw that outside the North Pole was just a copy of C. And then so if we think of North Pole as infinity, we sometimes think of that as C union infinity. I've changed my notation. So we had coordinates that we called W and W twiddle, right? There. Okay. So the easiest line bundle to talk about is actually not the tangent bundle that we saw, but just the trivial bundle, which is just a cross product of P1 cross C. So it's the same complex line at every point. So I don't know, maybe it's better to draw this way, P1 C. Then a choice of number in C at every point is just a function. So a section is just a meromorphic section is just a meromorphic function. So let's just take it to be some, could take a polynomial, for example. A polynomial on C, once you add infinity, becomes a meromorphic function on P1. And so let's say, just to take us as an example, take Z to the N. Oh, sorry. We're now calling that W and W twiddle. Take W to the N. If I want to look at the patch that includes infinity, I take W twiddle, which is 1 over W. So that's W twiddle to the minus N. And then the number of zeros minus the number of poles. You have N zeros here, counted with multiplicity, and N poles here. And so we get 0. So the degree of the trivial line bundle is 0, as you might expect. Now let's do the tangent bundle that we did before. Okay, I have my Z and W problem. Let's see if I can fix it for you. Okay, so W, let's take a meromorphic vector field. So that would be W to the N times the directional derivative in W. Oh, yeah, this is a bit of a mess because of the change in notation. So d by dw is d by dw twiddle, dw twiddle dw. So w twiddle was 1 over w, so we have a minus 1 over w squared dw twiddle. So that's, I think it's now, we've made the notation consistent now. So w twiddle is 1 over w. So d by dw is d by dw twiddle times minus 1 over w squared, which is minus w twiddle squared dw twiddle. Great. Okay, so if we look at this meromorphic vector field, it has n zeros at w equals 0. Now, if I look at the patch that covers infinity, I have to go to look at in the w twiddle coordinates. So I rewrite dw, d by dw in terms of d by dw twiddle. And then this becomes w twiddle to the 2 minus n. So this 2 and this minus n. Maybe there's a minus sign, that doesn't matter. So you see this has what? 2 minus n zeros. So the number of zeros, or thinking of as a pole as a negative degree 0, n minus 2 minus n, we get 2. So the degree of the tangent line is 2. Okay. So that's a little bit about how you can have different line bundles of different degrees and different vector bundles of different ranks.
Eric, I think there is a plus there actually in the degree, because otherwise the is n
yes,
plus.
I made a mistake. Let's see. Oh yes, sorry. The number of now what am I doing? Right. Yes, I'm thinking of a pole as a negative degree, so I'm a negative 0. So I'm counting them all as zeros. Yeah. Thank you. Great. Thanks a lot. Okay. Okay, so now we need to relate objects. So on the one side, we had these lines of rational slope, and on the other side, we had rank and degree. So as a recap, we have a line of rational slope. Let's call the slope d over r, just to be suggestive. And the line bundle is going to have, or the vector bundle will have some rank. So I'll call r and degree d. And actually, the map is going to turn out to be the slope. Actually, in algebraic geometry, the degree divided by the rank, they call it the slope. And they called it before homological mirror symmetry. So it's very suggestive that the map of objects should take the line of this slope to the vector bundle of that slope. So slope equals slope is our slogan. Okay, now we can answer our question from the start. We wanted the number of points of intersection of a line of slope 1/12 with a line of slope 12. And then from that, we could get the answer to our clock problem. That number of points of intersection is the dimension of the Hom space between these two objects. Therefore, it must be equal to the dimension of the Hom space between the mirror objects. So if we could compute that, we'd be good to go and solve our puzzle. So the Riemann-Roch theorem, which I won't prove, is a way to calculate the dimension of this Hom space between two objects of rank r and degree d, and another object e prime of rank r prime, degree d prime. And the answer is r d prime minus d r prime. So the rank of one times the degree of the other minus the degree of the first times the rank of the other. So if I plug in, so this is rank degree. Wait, what am I talking about? Sorry, no, degree rank. So then I get rank degree, so 12 times 12 minus degree rank, 1 times 1, which is 143. So that's the answer to our clock puzzle. We have 143 points of intersection. It's actually easy to calculate just geometrically, but anyway. 11 of those were in fact not ambiguous because they were the two clock hands were pointing in the same direction, which gives us 132. Of course, that's in a 12-hour day. An actual day is 24 hours, so that's our final answer. Okay, so we use the Riemann-Roch theorem and homological mirror symmetry to solve the puzzle. I'm going to do more than that, but maybe it's a good time to pause if there are any questions about it.
Sorry, what's the chi of E prime? Is that Euler characteristic? What I think I missed what was the
yeah, so that, yeah, I shoved a few things under the rug. Technically, it's the dimension of the space of sections of Homs from E to E prime minus H1. So in the case where, in the generic case where H1 is vanishing, then it's just the dimension of the space of homomorphisms between those two vector bundles.
Thank you.
Thanks for the question. Yeah, this is more swept under the rug. I guess what I'm really saying is that the answer to the question that we're asking from the algebraic side is just this. Okay, so now I want to do that sample calculation. There's just because there's a much more richer structure involved when you include not just what's the dimension of the space of HOMs between two objects, but how do they interact? What do the compositions look like? So we're going to try that sample composition, namely between P composed with P in that picture. Am I going to repeat the picture, or is it? Let me just see. I'll go back to the picture. Yeah, so I want to compute the composition of P and P. So P in HOM L1, L2, and P in HOM L0, L1. It's going to involve a sum over triangles like that. I don't know much about those triangles, but I know that they have to have slope 0 here, slope 1 there, and slope 2 there, because that's the boundary condition on the triangles, that it has to lie on the brane L0, which has slope 0 for one piece of it, the brane L1 for one piece of it, the brane L2. That was going back to what these triangles. They were the boundary conditions of these configurations. You had alpha, beta, gamma, and these holomorphic triangles satisfied those boundary conditions. And for us, alpha means line of slope 0, beta means line of slope 1, gamma means line of slope 2, or maybe 2, 1, 0. Okay, so let's go back to the calculation. We want to compose P with P, and the answer is going to be something in HOM L0, L2, and we saw that that was two-dimensional. And it's generated by the lattice point, P, and the sort of half-integer lattice point, Q. I'll remind you, Q. Sorry for jumping. This is the Q. It lives at the point 1/2, comma 0. Okay, so the composition must look like this. Now we just need to figure out what A and B are. What are A and B? Let's compute on both sides, sort of. So what is P lies between HOM L0 and L1, and so must be a homomorphism between a degree 0 line bundle and a degree 1 line bundle on this complex plane modular lattice. Well, a homomorphism from the trivial bundle to a degree 1. Well, the trivial bundle was trivial. So it has, if I just think of the constant function 1, that 1 is the generator, is the basis element for the vector space at every point. So when I look at a homomorphism of one line bundle to another, I have to send that generator somewhere. And where I send that generator is now just a choice of a non-zero element of the line. Well, it doesn't even have to be non-zero, just a choice of an element of the line bundle where I'm mapping it to. But we said that a choice of an element of the bundle at every point is the same as a section. So homomorphisms from the trivial line bundle to some line bundle is just sections. What that means is it's a choice of an element of the line at every point. Okay, so what is a section of a degree 1 bundle on C quotiented by a lattice? It's going to be a function on C. So think of it, C mod the lattice, as maybe lift that up to C. So then I just get a function on C. And when you lift it up, it turns out you can make it invariant under translation by 1, but it twists in a certain way under translation by tau. So it's not a doubly periodic function. A doubly periodic function would just be a section of the trivial line bundle. It would be a section, it would be a function on C mod gamma. Doubly periodic function would define a function from the quotient. So it's not that. That doubly periodic function is a section of the trivial line bundle. A section of a non-trivial line bundle is something that doesn't have a double periodicity, but somehow twists around one of the loops. And those twists are specified under tau. So here's the answer. It's a famous function called the theta function. Won't go into that theory. But there's one of them. There's up to scaling, there's a one-dimensional space of such functions, sections of a degree 1 line bundle on this, it's called an elliptic curve, this complex plane quotient by a lattice. And here it is. That's a formula for it. Maybe a comment. You can see invariance under z goes to z plus 1 immediately. Under z goes to z plus tau, it's a little more complicated. But it's not invariant under z goes to z plus tau. And that tells you it's not a section of a trivial line bundle, but a section of a line bundle that's non-trivial. It has some sort of twist. In fact, it's a family of sections. It's one for every tau, because you have tau dependence. So this is true in families over all tau. Okay. And so P, which was our unique intersection point of the line of slope 0 and the line of slope 1, is going to correspond to our unique up to scaling section from Ham, let's call it L0. L0 of degree 0 to L1 of degree 1. Okay, so notice we didn't just have to map the objects to one another, because the category has more than objects. It also has morphisms between objects. So we had to map the objects to the objects, and the morphisms between two objects to morphisms between two objects. And the morphism between L0 and L1 are described by this theta function. Okay. Okay, now we need to map what does the composition. Well, the composition is this complicated map sum of triangles on the left side, but on the right side, it's much easier because we're composing, in this case, 1-by-1 matrices. This 1-by-1 matrix is mapping the basis for the fiber of this line bundle to the fiber of that line bundle. And then if I have a third one, I just compose the 1-by-1 matrices, which is multiplication. So luckily, although this was much harder to describe, the composition is easier to describe. It's just multiply these two. And now, I mean, so like there's some double sum, and it actually can be expressed in closed form by using the same function. Remember, Ham L0, L2 is two-dimensional, generated by P and Q. On the algebraic side, those two sections are described by the same function, except with a 2 tau and a 2z. Pretty much the same function. I've written theta twiddle because there's a slight shift in there. I think that you put a 1. I mean, I know you put a 1/2, n plus a 1/2 there, but essentially the same function. So what we need to do is multiply this function with itself and decompose the answer as a linear combination of this function with 2 tau and again with 2 tau and some shift of 1/2. So that's an algebraic problem that can be done. And this is the answer. The A, I'll just tell you the answer for A. The B is the same with n goes to n plus 1/2. This A is this same theta function at 2 tau, but evaluated as z equals 0. So that would be a sum. If I put in z equals 0, this part goes away. Sorry, let me do that. If I put in z equals 0, this part goes away. And if I put in 2 tau, it becomes just that. Okay, so we've calculated on the algebraic side one of these coefficients in this composition. And what we need to check is that we would get the same answer on the A side, on the symplectic side. Okay, so I've set up the calculation. That's what I plan to do next. Algebraically, these holomorphic sections of these line bundles are described by this theta function, which enjoys this identity, which I'm just sort of importing for you, that when you square it, it can be written as a linear combination of itself with tau goes to 2 tau. And the coefficients of that linear combination are known, and this is one of those coefficients. So our task is to compute on the A side, the symplectic side, where we have to count triangles. What is this A? What is the sum over all of those triangles? Well, let's compute it. Any questions?
So A, B
Okay.
are different from each side?
A and B? Good question.
Different
So
from each.
what do you mean from me? This A should be the same as that A. If I've done things correctly, namely, if we've somehow guessed correctly which objects correspond to which objects and which Homs correspond to which Homs, then the calculations have to be the same. That's the equivalence. So if P actually corresponds to L0, and this P, which is the same notation, but it lies in a different Hom space, actually corresponds to, sorry, I made a mistake. If L0 corresponds to script L0, right, degree 0 line bundle, the trivial one, and L1 corresponds to the script L1, the degree 1 line bundle. And this P, which is in some Hom space, corresponds to the generator of the one-dimensional Hom between L0 and L1, which I've called theta. So the P corresponds to theta. Whoops, this P corresponds to theta. The other P also corresponds to theta. Then their product, or their composition, should correspond to the composition of the thetas. That is this linear combination. Now, I'm also making the assertion that this P corresponds to that theta, and this Q corresponds to that shifted theta. With all those definitions, this A must be equal, not correspond, now equal as a number to that A. Right? So that's what we're about to check. Well, we have a prediction that it should equal this quantum. So let's see if that's true. Does that make sense?
Yeah.
Okay, great, thanks. Okay, so now let's count those triangles. Well, I need a PPP triangle because my boundary condition to look at the pth entry in the composition of P with P, it means that my triangle must have vertices lattice points and then have slopes 0, 1, and 2. Oh, sorry, that's a bad picture. I think 0, 1, and 2. P, P, P. So what are all the possible triangles like that? I've drawn them here, right? Slope 0, slope 2, slope 1. Maybe there's some aspect ratio here, but it's pretty close. And this must be a lattice point, this must be a lattice point, this must be a lattice point. So up to translation, I might as well take this lattice point to be 0, 0. Now, if this is going to be slope 0 and that's going to be a lattice point, that must be n comma 0 for some integer n. Okay, and now I go up by slope 2 and I calculate, well, I get n comma, oh no, not n comma 2n, 2n comma n. I think that works out, right? Yeah. So because then I add, wait, no. Sorry. I'm doubting myself. I was right. But it's good to check. So what am I doing? If I add n this way, this has to be 2n. I should have made my pictures more to scale. And that means that that's slope 2. And then I get to the, oh, it's 2n comma 2n. Yeah, that's right. And now this is slope 1, and this length here is 2n. And so this is 2n comma 2n. All right, good. All right, so we did it carefully. We got the right answer. Thankfully, we had time. Okay, so these are all the triangles. And let's sum them up. So we get the sum over n, e to the 2 pi I times this area. That area is 1/2 base times height. So it's 1/2 base, which is n, times height, which is 2n, times the area of a unit square, which is tau. And so I get what? E to the 2 pi I n squared tau, which is exactly this answer. So that's a demonstration that homological mirror symmetry, there's a lot of actual calculations behind it. And that if you map the objects correctly and the morphisms between them correctly, then it's the statement that all your calculations are equalities. There's a vast number of equalities to check. But actually, this is the fundamental one. Using this one and in enough, let's see, using it judiciously, you can reduce all calculations to this basic one. So that's it. So I think it's pretty amazing. And that was just one part of one composition for one triple of objects. So homological mirror symmetry is established for this in some other spaces, and it's what we think is the core mathematical distillation of the physical equivalence of mirror symmetry. All right, that's probably a good place to stop. See if there's any questions.